Now, let's take a more detailed look at specific stations designed using water. And the first up is pumping from a well, a submersible well pump. Um, a common way of doing it is to have basically a steel plate mounted on the well flange, and that plate has welded to it a short spool with an elbow on the top and a flange, whatever, so that basically that plate is supporting the weight of the piping, the pump and motor, and of course the water that's in it, and the check valve that's down there. It's a common arrangement if you're going to build a pump house over it, which is fine. And if you're doing a pump house, then the electrical and control equipment can be in it. There is another way to deal with well pumps, and that is to use what is known as a pitless adapter. Now, if you look at the drawing on the right, you'll notice this thing is welded to the well casings, and basically what it has in it, so everything from almost the bottom up, like about where A is there, is where the pitless adapter would be welded or whatever to the uh, well casing itself. And what the pitless adapter has in it, you'll notice that there's two O-ring seals. The upper one and its seat are a bit larger than the bottom one, so that whole assembly, not the part that's welded, but the inside, you see the pipe where there's B and everything else, that whole inside assembly can be lifted out. In other words, to remove the pump, they take the cap off at the top, marked Z, Z, whatever, lift that, take that off, raise the pump up, clamp it when they get it up. There's using clamps to hold the pipe. This is a fairly common procedure for vertical turbines and submersible in wells. Basically raise that whole assembly up and then remove it, then come up, pull a pipe, pull pipe, pull pipe, and along with it, the wiring and everything disconnected till you finally come to the pump and everything lifted out. It's very similar in concept to the idea of a drop-in submersible wastewater pump, where the piping stays put, you just pull it out. This thing here, again, is the whole internal assembly can be pulled up and raised. And it has provision for cable to go past that discharge piece. You can get it with check valves mounted right about, again, where X's have check valves mounted on that. I wouldn't do it. I wouldn't do it. Far better, I think, to have a decent check valve down pipe length away from the submersible pump. But this can all be buried, as you can see on the picture on the left, can all be buried. Then all you need is your control and electrical distribution equipment, which can either be in a separate house or in a kiosk. Now, the next application would be, let's say you're pumping out of a reservoir. And for very small pumps, in other words, where a 4-inch submersible will do the job, they can be suspended in the reservoir and pumped from that, or can be in a dry gallery using cans. Same concept, pump doesn't really know where it is. You've got to just ensure, though, that the pump inlet with a submersible is always flooded with any pump. Now, anything larger, close coupled vertical turbines are most appropriate, either suspended and pumping directly from the reservoir or mounted within an adjacent inlet barrel in a dry gallery. When that's done, a below floor dry gallery is provided for the pump inlet barrels, but appreciate these units are designed to be supported from the top of the barrel only. That's an interesting thing. That is fairly common in our neck of woods, where basically you can see the inlet line from the reservoir has been run to two pumps with a line in the middle. I'm not even quite sure why that's for, but anyway, with these pumps, what had been done in the past is basically at the very bottom of that picture would be a base plate, and then another base plate that you can't see above floor level. The problem with that is that these steel pipes will tend to expand and contract and eventually try to pull the base plate away, either at the bottom or more likely at the top. So the best approach is to have that thing essentially floating, not tied to the floor as it goes through the floor, a rubber seal or whatever, so that it can move a little bit. Now, where submersible pumps are mounted and suspended directly into the reservoir, a motor shroud may be required for motor cooling. That comes down to some submersible motors require a minimum cooling flow over them, over the motor. In a well, that's fairly easy. In this application, where it's in a reservoir, it would tend to draw straight out from the inlet and nothing over the motor. So you put a shroud over it, and the shroud fundamentally is almost like we talked about canning, where you've got a plate and everything. You can basically follow that same approach, except with nothing at the bottom. You'd extend that down over the motor itself, and you really don't need to be too fussy about how the cable's coming through. But basically, that will ensure that most of the flow does go over the motor to cool it. Now, and the comment being, particularly with vertical turbines, because they're the flow rates are, we're doing it because they're higher, you have to be a little concerned about what flow patterns are getting to those pumps. So you don't get vortexing and inlet flow rotation, which can be problematic. And here's a war story. A large wastewater treatment plant basically took partially treated sewage, uh, not any significant solids, and they were being pumped to a biofilter or trickling filter. And the interesting thing was that overnight it was not uncommon for one of the pump motors to trip on overload. But when the following day the motors were tested, you found them well within limits. They were not overload. So I had a bit of a hunch. So basically, what I had them do was fire up several pumps together to see what the flow patterns in the wet well were like. And the inlet was off to one side of it, so that basically it did create looking down a clockwise swirl pattern, which was exactly the opposite of what the pumps were, counterclockwise looking down. And the flow pattern, as it got pumped down and fluid was coming in, it was such that the ladder looked like it was off a boat. There was a weight being picked up by that ladder, fairly significant. So you can see the problem, as we mentioned before. You get a situation like that, the pumps overperform, draw excessive power, trip on overload. Solution later on, they put almost like inlet barrels with a top deal so that the pump is shrouded, and the effect of the swirl the pump didn't see, and they didn't overload anywhere. Now, when you've got vertical turbines pumping out of a reservoir, the piping setup is pretty straight. As you can see here, or in the adjacent shrouded, pardon me, canned vertical turbines, as you can see, basically on the upper level or whatever, there's the pumps, the discharge, the inlets aren't right there. Therefore, it's quite easy to be able to walk around the pumps, get at all sides of the pump, and to get at the valving. Now, here's a drawing of a similar type of situation to that. And you can see, because the submersible or the vertical turbine pumps are drawing out of cans that are down below, so at operator level, everything is nice and open. They've used pump control valves. I'm not a big fan of pump control valves between soft starts with soft shutdown and variable speed. I think the days of pump control valves are pretty much over, but that's a personal opinion, whatever. But it's easy to get at those valves. Now, the one thing you notice in the picture, and I made note of, on the side there, I think it's trying to be a relief valve. They've got a control valve, a automatic control valve, mounted so the shaft is horizontal. Don't do that. They're a bear to service, and you have to worry about differential across it. We talked about that back in that section. Don't do it. Again, looking at that station, and the grading seems to have lined up where the isolating valves for the pump barrels or cans are. Not the greatest, but anyway, you can see it is quite easy to get it at the control valves, and there it all be. This picture here shows these are, I think, 500 horse motors, if I recall, and they're pumping out of what's known as a Fellman well, which is anyway. Without getting into that, these vertical turbine pumps are somewhat restricted as to how far apart they could be. All three of them are pumping out of this quote well unquote, which is obviously fairly big diameter. But it's enough to sort of cram them together. So to give better access, the discharge header was actually dropped down into a trough so you could get at that end of the thing as well by just walking over there. And as you can see, the electrical controls were put in the same room, which is usually not a problem at all. Pressure source. If we've got a situation where we are have a pressure source, in other words, the supply is not out of a reservoir but is actually under pressure from a distribution system or whatever, you can take small can submersible or vertical multi-stage VMS pumps, um, and they are designed to have some inlet pressure. Can submersible, that inlet pressure it almost doesn't matter what it is. It can tolerate it quite well. Watch out if you use a VMS, which are nice little pumps. Watch out for their maximum allowable inlet pressure because they do have a limit as to how much they can tolerate. Now, for anything larger, as I say, use vertical turbines mounted with an inlet barrel is the common approach. Station layout depends on the configuration. As we see before, you've had a discharge head and then a lower connection into the inlet barrel itself. It doesn't have to be a flange, it can be whatever. But you've got a barrel and the inlet is down at a different level. You also can use T-head pumps. And we'll get to T-heads in a minute, T-head on a vertical turbine, okay? And they have some advantages. Now we're showing here again where these pumps are being fed, as you see on the drawing on the right, they're being fed from vertical turbine pumps mounted in an inlet barrel or can is a common expression, and discharging at a completely different level. And there you can see access to the equipment, the pump itself and check valve, whatever, is fairly easy because you can walk in between the pumps and whatever. Here is a T-head. We talked about T-heads, where the inlet is not into the barrel. The inlet is into the head itself, which has provision to take that inlet, drop it down, and then discharge through. They're very nice, very clean, very simple. The only thing is you've got the situation of having an inlet and discharge on the same floor level. Now, to get access to the equipment, what do? You basically have three choices. Number one, elevate the header. You could also elevate the discharge, but I think it works better with the header being elevated. We'll take that for a start anyway. It has to be elevated enough that you can walk under it, in which case, yes, you can get access to all the equipment. The next choice is to have the header, as you saw in that one picture, placed below. There it was the discharge, but here an inlet header placed down in a trench. So again, you can get at the equipment by simply walking down. Or number three is a balcony. In other words, over the inlet header, you've got a floor with a ladder that allows you to get down between the pumps. And I'd mentioned with the ladder the use of what they call Laperi stairs. And what Laperi stairs are, they're kind of different. They're not like a regular set of stairs, and they're certainly not a ladder. They do allow you to access or come down the stairs looking forward. And what the trick with them is, you notice that there's sort of like every other step missing, so you got room for your knees. And I have walked them. They really are nice. They really work very well, and yet they're fairly compact. So, highly recommend it. Now, if you don't do that, and here's an example of don't do, if you don't have either the header raised, the header lowered, or have a balcony, you run into the situation where in order to get, like the end pump, maybe not so bad, but any of those other pumps, you're going to have to either get over or under that header that runs there. In this case, I think it's a discharge header, but you're going to have to crawl either over it or under it. And that is a pain in the butt. Same with the photo on the right. Again, you can see the discharge. You can see the problem getting at the equipment. You've got to jockey over or crawl under. How low can you go? Maybe if you're a limbo specialist. Anyway, what do you do for control when you're pumping into open discharge? Most of the time, you'll have level control at the reservoir, which can be either an uncontact transmitter like ultrasonic above the water level, or a pressure transmitter located somewhere remote from the discharge line, as mentioned before, like a drain line. With wells, if you're sourcing from a well, I mentioned even though you give up that 5% of efficiency by the use of the drive, um, it has advantages for submersible pumps, such as we've mentioned, wide range of controlled ramp up, ramp down, ability to control well at a set drawdown at a set level. That is a big thing, and it goes into how to do it. And if you need it, single to three-phase conversion using a drive. Now, one of the things you'll find there are suggestions in requirements for using a submersible well pump motor, and one of them is because of that Kingsbury plate bearing at the bottom. Think of somebody on water skis. The motor needs to accelerate quickly from 0 to 30 hertz. That allows the plate to immediately get up on the surface of water, as I say, like a water skier, and away you go. Similarly, from 30 hertz down, they basically would like the pump to be freewheeling. Consult motor manufacturer for other recommendations, and I think you can pretty much cover all that. Now, if we're sourcing from reservoir source and power source, talking about electrical, adjustable speed drives have no real advantage unless you either, number one, want a really long ramp down over 30 seconds, a relatively low force main static head to friction ratio to minimize water hammer. Smaller pumps can operate just fine across the line, while solid state soft starters with soft stop will reduce not only inrush current on starting, but again, this ability to soft stop, which usually does a fine job of taking out water hammer if there's a high static head to friction ratio. Okay, you can play that game for up to 30 seconds. Going back to the previous one, pumping from reservoirs, not only water hammer, if you've got a lot of friction on the discharge side, then you might look at playing games using variable speed to kind of average out your flows and improve efficiency. But as I say, drives by themselves do not automatically give you improved efficiency. Now, pick a pump, closed discharge. Where we have a pressure system, here's a little guideline as to how to use it. Pumping into a closed pressure system inherently difficult due to the changes in flow rate. And again, most problematic is just zero flow. And in a closed system, unless it's a very big one, you're going to run into that. And again, nearly any form of kinetic pump could be used, but flat system curve is ideal. Looking at the little guideline chart over here, well source, small submersible with a hydropneumatic tank only from a well. Because beyond that, a small submersible where you can have hydropneumatic tank or tanks to start and stop, you really shouldn't be pumping into a closed system. It just shouldn't be done. Now, if we're talking from a reservoir into a closed system, either a jockey and suction or your double suction split case, same thing with if you've got a pressure source. And in both cases would recommend variable speed because it allows you to control what the discharge pressure is. And I would slightly make sure the pump's got a little extra head and a little extra motor, not dramatic, but a little bit. Then if the operator is operating the thing and people are saying, no, the pressures are low, he can literally just go over and just dial up the setting, the discharge pressure setting, and the problem is solved. Magic. Let's go in a little more detail here. Well source. And as I say, except in those situations where you can use hydropneumatic tanks, and they're big, essentially a reservoir, that's about the only option you got. And I mentioned, of course, with hydropneumatic tanks, you can manifold them in parallel to get more draw-off capacity and, of course, redundancy. If you've got 10 tanks and one has to be replaced, you can live with that. In terms of beyond that, a reservoir source, pressure source, smaller applications, this is flat curve or pressure system discharge. For smaller applications, conventional end suction pumps can be utilized. Typically, they have very flat head curves, but should be operated at about 1800 less slippage, of course, or less to reduce noise and minimize radial thrust relative to pump size. This puts your head capability below 200 feet as a rule. Now, if you really want to use end suction pumps because they're simple and nice station layout, but conventional 1800 RPM won't do the job, there is an industrial approach. And I think I'm going to make a stop for a moment there. I think that's the one thing we're trying to do. It's like hollow shaft versus solid shaft motors. One is municipal, one is industrial. No, no. Look at applications. Maybe you're using the wrong pump because it's been traditional. In a case of solid versus hollow, I would agree. Look at what else is out there. And one of the tricks here where you want an end suction pump, but you really need to pull some head. ANSI D73.1 is a specification, and pumps designed to that basically are industrial pumps, chem standard or whatever. They have reliable head performance at 3600 RPM that will give you the kind of heads you're looking for. They're a little different. They have oil lube bearings, which is a good thing, but you ain't going to use a grease gun on them. And they are noisier. The motor probably being the biggest thing, but they are noisier. But there's another option if you want to go that route. And here's the layout advantage of an end suction. You can put the discharge header above the inlet. You're going to need some custom pipe supports, but it gives you the advantage that it's very compact. These motors, of course, end suction, you should have a spacer coupling. But again, it's easy to get to the equipment by simply walking around. Double suction split case. Say they're almost like two end suction pumps back to back, the impeller in these things. They have relatively flat curves. They can tolerate radial thrust. They're designed for it. And good serviceability. You pull the top off and everything's exposed. And broad available performance ranges. Typically operate at 1800 RPM, but 3600 RPM, again, well noisier, and again, it's the motor, it does remain a practical option if you need it. And here's a little graph put together sort of showing what we're looking at. These graphs, by the way, are put together using Alice Chalmers because I'm familiar with what they had. Alice Chalmers was bought out by ITT, which owns Google, which owns Fligit, as I call it. But anyway, and they had a very broad range of pumps, so it's a pretty good guideline about what is available on the market. And as you can see here, end suction, you can go beyond 3,000 gallon a minute. There's lots of selections out there, but your heads are going to be down under 200 feet. If you need to go above that head, particularly at the left-hand side, you can go to a ANSI B73.1 two-pole, and that can pull you up, as you can see, over 600 feet. They're noisy, but they work, two-pole. Anyway, or double suction split case, two-pole. Or if you're looking for big capacity, big head, then double suction split case, four-pole. And there are a lot of selections available on the market, okay? Now, double suction split case, one of the problems is how do you mount the things? Good to have an inlet header, which is large enough to act as a plenum, so you can make the bend from the header into the pump without worrying effectively of seeing the header as a reservoir. But you end up, there's really no other option than to mount the pumps in line. That's about the best work. But then you've got that thing of having to either go over or under a header. So again, we go back to this approach. You've got three options. Elevate the inlet header and appreciate coming down like that. That elbow at the bottom is not a problem to the split case pump, not a problem. It's elbows that are in the same plane as the shaft that cause a problem with unequal inlet. This is just fine. So you've either got an elevated header that you walk under, and this is kind of a picture. This is a package that was being built in a factory, and there is the discharge header, except you'd want that elevated enough for people to walk under it, and you can crawl under it fairly easy, but it could go higher. Anyway, another option is to place the inlet header in a trench. You walk over the trench, and there you can get it, the pump and the discharge check valve and all that good stuff. Or a balcony arrangement, um, which you can see, and again, consider LePerry stairs. There is where the inlet header has been put into a trench, and as you can see, to get at everything is absolutely no problem at all. Here's a picture where they have a platform. Now they've used conventional stairs, and you can see that does put it quite close to the pump itself. If they went LePerry, you could almost cut that distance in half. One of the problems with closed systems is the situation of no flow. And unless it's a huge municipal system, that can happen, particularly at night or if somebody accidentally shuts a valve somewhere. And the best approach is to have a jockey pump. The little vertical multi-stage work great, and hydromatic tanks. When flow demand is minimal, the jockey pump will operate continuously as the lead unit, speed being automatically adjusted to maintain a constant preset station discharge pressure. That's what you've got to drive on it for that reason, simply to control pressure. And it's not a very expensive drive on a small pump like that. Now, if you've got a reservoir available, what you can do is have a circulation line from the discharge to the inlet of that VMC pump and put in a temperature sensor, so that when the temperature gets up to about 60 degrees C, about 150 Fahrenheit, it'll open a solenoid and allow discharge flow from that loop directly into an adjacent reservoir, assuming you've got one, if you're pumping from a reservoir. This way, the jockey pump will not be damaged from overheating. And once it's been triggered, let this valve stay open for about 5 minutes to let everything cool down, and then back we go. The ideal approach with hydropneumatic tanks is basically you run the jockey pump as a cycling unit. In other words, when flow demand is very low, measured by a jockey pump flow meter, and yes, a little mag would do that very nicely, the pump will be stopped. Then it'll remain stopped until water taken from the hydropneumatic tank or tanks eventually causes the discharge pressure to fall, jockey pump starts up again, and away you go. Realize with the hydropneumatic tank and the fact you're using a variable speed drive, cycling is not a big deal. Even ramping that small pump up in a few seconds, say 5 seconds, is nice and gentle. The motor is happy, so your number of cycles is not a big thing, and it doesn't take much of a hydropneumatic. You really don't need to size the hydropneumatic tank to minimize starting and stopping. Okay, fire flow. Pumping into a closed system, very often you run into the question of needing fire flow. Now, if you've got a number of pumps, say split case, whatever, and they're big enough, then you just simply design that into the station that it can meet what is fire flow along with the peak demand of the system. If not, if the system demand is relatively low, then you may need to go to a dedicated fire pump. Now, because it's not, by the way, why did NFPA and listing with UL and FM, why did they do that? Insurance. FM and UL both basically are groups of insurance companies. That's the labels that are used. And NFPA 20 standard requires listed pumps, but in this case, you're a municipality, you really don't need to do it. However, specifically the performance that says shutoff head shall not exceed 140%, that's straight out of NFPA 20. You would want to make sure that the fire pump you're using meets that. And another interesting thing, with NFPA 20, they require a circulation relief valve for all horizontal pumps. It is not actually they call it a casing relief valve. It is not actually a pressure relief valve as we would think of it. It's too small to actually have any significant effect on that. What it does is it serves to cool a pump when operating close to shutoff head by flowing water to waste. Okay, fire pumps are intended for intermittent service only. Now, something about those direct acting valves. Classically in the business, they use direct acting relief valves. But direct acting relief valves on those things can be problematic because a direct acting relief valve, once it opens, the pressure has to fall to about 80% of that. In other words, if you're tripping at 100 psi, it has to fall to 80 psi. And a better approach is to get a suitably sized automatic valve relief pilot, which is a direct acting valve, but instead of just using a seat with a spring behind it, it actually has a diaphragm which is much larger than the seat. Therefore, its control is much, much, much more accurate than the typical off-the-shelf, cheap and dirty direct-acting relief valve. Opening and closing very close together. Um, Example, Clay Sea. They should be 3/4 inch for pumps rated up to 2,500 gallon a minute, and 1 inch beyond that up to 5, which is 5,000 is the limit of NFPA 20. When inlet pressure may arise significantly, let's say this fire pump and it's a system where it's supplied pressure and that inlet pressure can get up there, uh, you can get to the point where the pressure gets so high that actually the relief pilot you've got described above will actually trigger and just waste water. So how you get around that, and by the way, classic problem in Vancouver with fire pumps was that because although they're designed for something like 20, 25 pound minimum, city water pressures a lot of the time are over 100 psi. So the stupid little relief valve would see that, oh my God, the pump is closing in on shutoff. It would open up and sit there and waste water forever. The way around that is simply to use a differential automatic valve relief pilot. And you can get them. People like Clayval and whatever, you want a differential automatic relief pilot. And it looks at the difference between inlet and outlet pressure, and you set it where on the curve you want the thing to open, and your problem is solved. Electrical, reservoir source, pressure source, be it end suction or split case, adjustable speed drive. Why adjustable speed? I mentioned because then you can dial in the pressure that people want. And with those, of course, you've got the advantage that ramp up, ramp down is no problem, and you want to play phase converter, you can do it. Duty pump operation should be controlled by flow-based sequencing, and it outlines that whole thing in theory. But let me just show this chart here. Basically, you've got the lead duty pump stopped when you get down to the point where the jockey pump can take over. As flow rate demand goes up, you restart that lead duty pump, then the flow goes up, lag duty pump, start, and then standby duty pump start. Okay, and as you go back down, you can see how it's logging them off to essentially have the right number of pumps to match the flow demand that's there. And one of the little tricks you can play, by the way, is sequence it. So if the pumps are all identical, you can actually have sort of a first on, first off arrangement, so you get some cycling in amongst the pumps over time, which I've just explained here. One thing to consider, while a signal magnetic flow meter, reduced port sizing, can provide accurate flow set points, it's worth considering having perhaps individual flow meters sized to have a decent flow rate, monitoring the velocity for each duty pump. The control system can easily totalize them. If you know how to program a PLC, you can have them totalized. And not only does it simply give you the ability to test one pump by itself, but you're going to get better low flow accuracy because they will be smaller magmeters. And again, you can jump velocity, which is what those things are like. Fire flow. If you've got a dedicated fire pump in an application having normal low flow demands, again, NFPA standards don't have to be met, but you may want to consider reference to the document and use a listed, in Canada, CUL, USUL, or FM controller listed. That way, if the issue comes up, you can say to people, look, we actually are using a listed fire pump controller. And that is about it. I hope you found that of interest.